Hello everyone, welcome to the second topic, reservoir fluids and volumetric estimation. So today I will quickly do a review of the class today since there's lots of content, but I'm pretty much sure you already have pretty good background about it because most of the topic we will actually cover are the basic chemistry and the physical chemistry actually, and the petroleum in a petroleum point of view. So the reservoir fluids. So in the oil and gas reservoir, what types of fluids actually we have inside the reservoir? So we all know we got the crude oil, but the crude is a mixture. It's a mixture of lots of different types of components. Okay, so there could be alkenes, alkynes, and naphthalene, different types of aromatic. So all are the type of hydrocarbons. Okay, so the alkene or the paraffins are the single chained, as you know. Okay, and single chain means like, you got only one chain. So the example could be like methane, ethane, propane, hexane, ecane. Okay, so these are all the paraffins and single bonded, as you can see in here. Now in case of alkene, okay, so it got double bonded. However, within the alkanes you can also have the single bonded but with the branches. That's what we call the iso. Okay, like the isobutane or isopentane, the branches like that. So it could be just like the linear chain, or it could be the like the bonds like that. So for the alkenes, we also it's also known as the olefins, or like the double bonded. Okay, and acetylene or alkynes are like the tertiary, or like the triple bonded. Now in the reservoir condition, as it's actually in very high pressure and high temperature, the percentage of alkene is very low in there, because most of the alkenes actually cannot stay at that high pressure and temperature, so it converts to alkanes, and likelihood of presence of alkyne in reservoir is very low. Okay, and that's the things. And there's the problem of alkynes, because if it presents in long chain, it can form solid into the pipeline. So it's we always need to avoid. Now the other types, we have like the naphthene, benzenes, and different types of aromatic. Benzene, they are not very reactant, but it is a known carcinogen, and this structure of benzene and its derivatives like toluene, xylene, ethylbenzene, and many others. Okay, now since we told you like that crude oil is a mixture of all of these different types of oil, so we need to distill, and the process actually known as the fractional distillation, as many of you already know. So what is the fractional distillation? Fractional distillation is the method that by varying the temperature we can separate the liquids. Okay, for instance, if you have a mixture of alcohol and water. Okay, for instance, you have a mixture of alcohol and water. In that case, the temperature, like the boiling point of water, is 100 degrees Celsius, whereas the alcohol is much lower, near 70 something. So if you actually heat up if you actually increase the solution temperature, then what will happen if it's go beyond to 78 degrees Celsius and more, then the uh, alcohol, like alcohol means like I'm talking about ethanol, it will vaporize, right? Or any type of alcohol, it will actually vaporize way faster than the water. Okay, so that's a type of the distillation we called, like the separation actually called like the fractional distillation. So we use the same principle for the crude oil. So in crude oil we have a wide range of hydrocarbons. We have from carbon 1 methane to C20. Okay, so like that. So methane, or like the lower the number of the hydrocarbon means it's more lighter. Okay, it's way more lighter, and the higher, or like the C20, or like the aromatics in here. Okay, so they are more heavier. So what happens if we have a long distillation chamber, and there if we feed the crude oil, and if we actually vary the temperature from the top portion is like 30 to 65 degrees Celsius, and at the bottom, the more one we go, we have a reboiler in here. Okay, and at the top portion we get a condenser. So the reboiler temperature, if we actually set more than 400 degrees Celsius, then what's happened, this reboiler at the down, it will actually keep the heat up. Okay, and the stage wise, if we decrease the temperature if we actually set the temperature in such a way, like in each stage the temperature zone is like this, like 30 to 65 degrees Celsius for instance at the top, then we have the alkenes, or like the methane, ethane, propane, like this gas. Okay, so these will be separated first, and then the petrol, like these alkanes of like from C5 to C8, these will separate like within 65 to 70 degrees Celsius, something like that, and then it goes on something like that. And at the bottom we got the residue, which is bitumen, is like pitch or tar. Okay, so these are more heavier, so that means the more top you go, the less density of the fluid. That means less density means more volatility. Okay, so these are more volatile, like methane, ethane, propane, these are more volatile. Now this pentane, okay, or hexane or heptane, so these are less volatile than methane or butane. Okay, so the things, and exactly that's how it actually goes on. So this is the main principle of the fractional distillation. Now when I talk about like this fractional distillation of the crude oil, now it is very important to know what is the percentage of gas actually dissolved in the crude oil. Okay, so as you already know, there is a portion of gas is dissolved in crude oil. Why? Because in the reservoir, the gas is already in very high pressure. Okay, so at this high pressure, the gas could be dissolved in the reservoir. Now, because of this thing, the gas could actually dissolve in the reservoir, in the reservoir fluid, in the crude oil. So there's a way that we can actually measure, how much gas actually dissolve in there, and this we called the GOR, or the gas oil ratio. Okay, so how we actually can measure that? We have a imperial and metric system, which is very individually different. Okay, so what we can do, we actually measure it, like the amount of gas to oil in petroleum is this ratio, like the standard cubic feet of gas dissolved divided by standard stock barrel. Okay, so this is how we actually measure. Now API actually developed a standard to determine the gravity, the specific gravity, of a crude oil. Okay, now here is the thing. Depending on the type of crude oil reservoir, the type of reservoir, the geology, and many other things, there's a wide variety of crude oil we found. For instance, give an example. In Alberta, we got oil sand, and the composition is way totally different than the Middle Eastern crude oil, and the Middle Eastern crude oil's composition is very much different than the Nordic, or like the Russian crude oil. So there are so many differences, right? So we cannot actually do a standard, like we just cannot say like the specific gravity of crude oil is this. For instance, the specific gravity of water is what? One. We know that. But in case of crude oil, we cannot say that. Okay, and we also cannot say such thing like, this is the how much gas could be dissolved inside the crude oil. We just cannot. We just don't know before doing a qualitative analysis. So what we do in this case, like API, the American Petroleum Institute, they actually make a kind of like a standardized way to explain the specific gravity. This we call it API gravity. Okay, so it is a dimensionless gravity. Okay, because it works with the specific gravity. This is the formula. Okay, and the only input of the formula is the specific gravity. And what is the specific gravity? Specific gravity is the density of oil divided by the density of water. That means it's became unitless. So that means the whole API density is unitless. So for instance, give an example. If we have a crude oil density of 800 kg per meter cube, then the specific gravity of that crude oil would be 0.8. Now, some of the crude oil could be 0.81. Some of the crude oil's density would be 0.8115. So dealing with this small number would be very tough. So that's why API actually developed this scale to make a broad spectrum. Okay, to make this broad spectrum, and this actually really works pretty well. Look at here, these degrees of API. That means in here you can see like gas, it don't have any specific API gravity, but a wet gas, which is actually like a gas condensate presence in a small portion of gas condensate actually presence in the gas, got the higher API density, and the gas condensate itself got like this API density, API degree, this value, and black oil got this one, and tar sand got API value of less than 10. So it is very much clear, like the density of the tar sand is way higher than what? Than the gas condensate, right? So that means it's inversely proportional, right? You can see the specific gravity and API is inversely proportional. That means if the density and the viscosity of a crude oil increase, then the API would be decreased. So this is an important chart. This chart you can see, like the initial gas oil ratio, what it could be, the range, the API density, and the specific gravity of gas, how it could be, and what could be the potential composition in mole percentage. Okay, so the heavier or the lower API, the thicker the oil. Okay, so that means the more oil got thick, the less API value we got the degree of API. We got. Now the natural gas don't have any API value. That makes sense because that would be something like infinite. So that's exactly why we don't have the API value. The thicker the oil, the no longer of the longer the carbon chain, as we already know. Okay. Now let's go to the another topic that's we call the phase diagram, which is very important. Now in reservoir, the crude oil is in very high pressure and high temperature, as we already know. But exactly, like, I mean, how much it is, or like, I mean, when you actually withdraw when you actually withdraw the oil and gas, then we actually change the temperature and pressure, right? So how actually affect? So we'll actually see with this phase diagram. So let's actually copy this to here so that I can actually draw some, and I can actually explain you a little bit. Okay. So sorry. So the phase diagram. Sorry again. Yeah. So the phase diagram is a diagram that it shows like a material which can be a solid, liquid, or in vapor. These are the three phases we usually got. Oh, actually, there are another phase that's we called plasma phase. Okay, we know any types of matter it can have three major different types of phases. Another is plasma, which is very rare. I mean, not in the earth. We actually see it's in the sun. Actually, it's in a very high temperature. The internal structure of the atom actually it goes away, and the plasma actually forms. So that's a different thing. But I mean, in the normal case, we have three different phases. One is like solid and liquid and vapor. Now, exactly like the crude oil, let's explain this phase diagram at first with a more simpler example with the water. Then we will actually correlate with the crude oil. Okay, so it will be much more easier to understand at that time. So what's happened? For instance, this is a pressure curve. That means if you go upward, and the more pressure, just 1 second, sorry, how we can do this, I think like that, yeah. So the more, if you go more upward, that means the more pressure you are actually increasing. Okay, so you are increasing more pressure, and this axis, the x-axis, if you go in this way, the more temperature actually you are increasing. Now, at the lower temperature, what will be the phase? It will be solid. For instance, I'm just giving you an example. Okay, for instance, this is water. Okay, in that case, what will happen? Like, I mean, at 100 degrees Celsius, sorry, excuse me, at 0 degrees Celsius, it will be an ice, right? At 0 degrees Celsius, at the normal pressure, it will be ice. So that means if we actually see at the phase diagram, so it will be somewhere in here. Okay, so that means if the temperature is 0, like here is the temperature, for instance, is 0 degrees Celsius. Okay, beyond that point, at any point, okay, for instance, is 0 degrees Celsius, this is minus 50 degrees Celsius, for instance. At any point, the phase would be totally solid. It would be totally ice. Regardless, if you actually increase the pressure, it would be still ice. And you know, like pressure and temperature, actually, how is that? Pressure and temperature is proportional. Okay, so we'll actually come to that later on. But yeah, So if you actually increase pressure, so that will be more solid, okay? And if you actually decrease pressure, it will be have more tendency to vaporize. Now from here, for instance, it is at 0 degrees Celsius, okay, here at 0 degrees Celsius. From here, if you actually move, like increase the temperature, that means moving in this way, then what will happen? The phase will change from here to here. There will be a change of phase. So it is called the melting point, okay? Here it is written, it is the melting point. That means the phase will change from the solid to liquid. And the more you will increase the temperature in this way, then what will happen? If you make the pressure constant, like you are not changing the pressure, you are just increasing the temperature, then what will happen? It will still remain liquid. For instance, this is 50 degrees Celsius, okay, it will still remain liquid. This is 80 degrees Celsius, it will still remain liquid. But at this point, for instance, this is 100 degrees Celsius, and then what happened? Then the first bubble will generate. The first bubble or the first vapor, okay, will generate. And the more you increase the temperature, then what's happened? It will be vapor, or we call it steam, okay, the boiling water, the steam. So at this point, at 100 degrees Celsius, the steam generates, okay. So this point actually we called bubble point. We'll actually see that later on, okay. Now probably you heard about this thing, like boiling water at the top of Himalaya is easier. Like you can actually boil the water at less temperature, okay. Probably you heard about it, okay. And why actually that happened? That happens because at the top of the Himalaya, the air pressure is significantly lower. So that means if you actually lower down the pressure, okay, then you can actually boil this water not at 100 degrees Celsius. For instance, you can boil it at 80 degrees Celsius. Okay, so this is, for instance, 1 atmosphere, ATM. Now at this pressure, for instance, 0.7 ATM, 0.7 atmospheric pressure, you can boil the water at 80 degrees Celsius. And at this point, like even if you actually decreasing the pressure even more, like at half atmospheric pressure, okay, like this is the regular atmospheric pressure we have right now. If you actually half it, then what's going to happen? Even you can actually boil the temperature at 50 degrees Celsius, okay. So this is actually the phase diagram. That's how actually it works. So at this point it would be vapor. Now if you actually increase more temperature, then at some point, at this point, here it is the steam, but still there could be a portion of liquid will be in here, okay. A portion of very small bubbles of liquid will be present with the gas, okay. So that's why we call it vapor. But if you actually increase the temperature more, for instance 180 degrees Celsius, I'm just giving an example, in that case the water you will have, it would be clear, crystal clear. It would be totally, it would look like air, okay. And that's we call superheated gas or superheated steam. Also in this case I'm giving the example of the water, the superheated steam, okay. And the superheated steam is something like that. It don't have any water droplet or any vapors in there. It totally looks like gas, and it's it contained a lot of energy, or we also call it HP gas sometimes, or like high pressure gas, okay. So, or like the steam we actually called LP gas or low pressure gas. You will actually need to know these things, because when you actually work in industry, you will heard a lot of like industrial terminology. Okay, so this is the HP gas, this is the LP gas, like that. So this is how actually this phase diagram works. Okay, now at this point, if there is a steam has been generated, if you actually decrease the temperature, then what's happened? At here, at this line, okay, when it touched the line first, that means like at this temperature, at 100 degrees Celsius, the first dew will create. Dew means like it's starting liquefying, okay, so that's also called the dew point at a certain temperature and pressure we have this time. So we'll actually discuss this thing later on more. Just remember like these important points, like this is a triple point. Okay, so at this point, like at this pressure and at this temperature, okay, this water can be in all types of phase. It can be like it can be it can present in all three phases altogether. I know it's sounds crazy, but it's like that happen. And here is the critical point. Okay, so if you cross the critical point, then what's happened? You'll get the superheated gas. If you actually increase the temperature, or if you actually increase the pressure, then you'll have a compressed liquid. Okay, so this is how it happens when you actually go beyond the critical point. Now this is the example I gave about like how the water in case of water, but in case of reservoir fluids it's a mixture. Okay, so the phase diagram actually is not that simple in case of reservoir fluids, for instance in crude oil. Okay, so we'll actually see how it actually works in case of crude oil. So all these things actually explain like what we have, what I have already explained in there. So please go through these slides and you can learn. So exactly this is the what I was talking about. Like I mean the crude oil product, we have a mixture of the product in the solution, and each different components of the crude oil has its own phase diagram. Okay, for instance heptane got its own phase diagram, or like decan got its own phase diagram, or methane got its own phase diagram, like that. Okay, so because crude oil is a mixture, right? So that's actually happened like that. So because each of the product contain the crude oil behaves differently at certain temperature and pressure, it's possible we will have a mixture of states, okay, at a particular pressure and the temperature. So please go through these slides. Like here is an example. Okay, what the phase diagram of a mixture could be. Okay, so this is a phase diagram for a single component, but for a mixture it could be looks like that. For instance, you are actually changing the composition and how the critical points and the dew points is actually changed, or the bubble points. Okay, so here is the one terminology. You can see the Cricondent term, and another would be the Cricondent bar. You will see the next one. So this is actually like an example of the reservoirs phase diagram. Now this Cricondent term, it is something that's the maximum temperature. Okay, you remember like this critical point, like beyond this critical point you'll only get the superheated vapor. So this is that's actually happened for a single component, but since in crude oil it's a mixture, so Cricondent term became the single point became a region, and here this is a point actually, not a region at this point. That means, and here it is the maximum temperature without 100% gas. That means the more you will go in this way, that increasing the temperature, that means everything will be 100% gas, and right after to that it is solid and vapor liquid mixture. Okay, Now, just like the cry-content term, we got a cry-content bar at this point. Okay, that means the pressure, like beyond to that, that would be totally a liquid. Okay, 100% liquid right after that. So this is the liquid and this is the dew point line, that means the vapor. Now why is that? Because if you increase pressure, the more you increase the pressure, then what will happen? The phase would be more like the percentage of liquid will increase. Okay, and the more you increase the temperature, however, then the percentage of vapor will increase, because if you increase the temperature, then the component will be vaporized, and if you actually increase the pressure, then it will liquefy. Okay, so this is the gist of this pressure temperature phase envelope for the hydrocarbon types. Okay, so the critical point we have explained, and the bubble point. Bubble point is the transition occur from 100% liquid to the gas liquid mixture. Okay, so bubble point means it create the first bubble forming in the liquid. Okay, so here is the bubble point. Beyond to the bubble point, it is totally liquid, and right after that, the first bubble actually creates for the different phase. Okay, dew point, the same with the bubble point, but in an opposite way. That means beyond to the dew point, it's gas, and right at the dew point, the first liquid dew actually creates. We already explained that, and we have seen like the liquid volume line and cry-content term, as I have explained already, and the cry-content bar is the maximum pressure that located there. So these are like the important points. Please read those. These are very important. Like what is the critical point, cry-content bar, cry-content term, and like the triple points and phases, different phases. Okay, so it's the thing. So this is a perfect example of the reservoir fluid, since it's the mixture. So different types of the components would have its own different types of the phases. Okay, so this actually shows the n-heptane to ethane, this from C2 to C7, these different for the different components, different phase diagrams in one chart. Okay, so please go through that, and if you actually read that, and you will actually learn more about this phase diagram, as we have already explained in here. So based on this knowledge, you can actually get it's self-explanatory actually what is happening, because as you know, like ethane is what least number of carbon, that means it is a gas, so it's more dependent on the pressure. That means if you actually decrease the pressure significantly and decrease the temperature significantly, so it might have, you can actually condense and make it liquefy. Okay, but if you increase the temperature slightly, then you can see the more prone to be the vapor in nature. But in case of n-heptane, for instance, it is more like robust. Okay, it is more like, if you increase the temperature more higher, then it's still like the phase diagram like that. It's not steep like ethane like that. Okay, now why this is important, why this phase diagram is very important. This is important. One of the reason is because if you are transporting the petroleum, then if it actually transfer in okay, let's give an example in for instance, the oil and gas is in the reservoir. Okay, this is the gas, this is oil, and this is water. Now this is, for instance, under 2000 meter. Now if you actually take out the crude oil from here, then what's happened, if you don't know like which phase it is, then when you actually try to take it out, it could actually expand, or the amount you will find could be much more lower even. Why? Because gas solution, gas actually dissolved in this oil. So for instance, you have imagined you'll get 200 barrel, but when you actually take it out, because it's in higher pressure, right, 2000 psi for instance, when you actually take it out to the normal pressure, then it could be something like 180 barrel. Okay, why it could happen? Because of these oil and the dissolved gas could actually go out from there. Okay, and that's how this oil could actually, the dissolved gas will go out, and that's how we can actually get a lower number in here. This is why we actually are interested to know how much gas could actually dissolve, and this is exactly why this phase diagram is very important. Another very important thing is, like, when you actually take out the oil, after that you need to transport it through a pipeline. Okay, now when you actually transport it to the pipeline, you have to maintain a certain pressure and temperature, okay, to transport it. Now this transportation sometimes happen in very high pressure, and when it actually transport within that time, if the pressure actually decrease, or if you actually increase the temperature, then inside the pipeline there could be some bubble actually create, and this bubble could actually severely corrode or erode the whole pipeline system. Okay, so this is one of the example. Another thing is, like, for instance, you you actually sell to your customer the crude oil, and you have promised it is a 1000 barrel. Okay, but during the transportation time, the vapor inside could actually go out, okay, from the crude oil. And when you for instance, from Qatar, you were actually transporting the crude oil to Busan in Korea. Okay, and what's happened, like, you can lose up to 3 to 4% volumetric weight due to this dissolved gas could actually just go out. So you have promised like 1000 barrel, but you got only, like, 900 something, like, for instance, 970 barrel. Okay, so that is a loss. So imagine, for, like, millions of barrels, how much you could actually lose. It's a huge amount of money. Okay, so these are the reasons we actually need to know about this phase diagram, and this is very, very important for our production, profitability, and the safety also. Okay, so this is like the main application. Okay, so please go through these slides. You will actually know how it works, like inside the reservoir, why this is a bad thing, we lost the value, and also there's a problem with this transportation also. Okay, now gas condensate. What is gas condensate? Gas condensate is the in the reservoir. Okay, there is a liquid and gas. Okay, there are two different phases. However, inside the gas, we have a portion of a liquid dissolved, and that's the liquid we can actually separate from the gas, and we can actually sell it, portion of the liquid. That's the portion of the liquid we called gas condensate. Okay, so in reservoir we can, so in the reservoir there could be like different portion of the gas condensate. So depending on the type of the reservoir, we have different types of gas, natural gas actually. Okay, so it could be the dry gas, which doesn't have any gas dissolved in oil dissolved at all. We get the wet gas, that means a low percentage of oil we have. We can actually just filter it out, and then we can actually have the dry gas, or we can actually increase the temperature and it could get dry. But we also have a gas with a heavy mixture of the liquid in there, that's called the gas condensate. Okay, and we have the volatile black oil, we have the black oil and the tar sand. So there are different types of crude we have. Now these are the dry gas. It got little or no liquid at all. It could be, the liquid could be oil or water. In Nova Scotia there is a chance of finding the dry gas. I will actually share an article later on about the gas prospect in Nova Scotia. Okay, wet gas, as I explained, there could be a portion of a heavy hydrocarbon is in there, but we can actually just collect and sold as a premium. And this is the thing, so about the oil and gas ratio and everything. Okay, now ideal gas law. So because there's a difference in temperature and pressure and the volume at the underground, oil and gas could be different from that above the ground. So we need to know the difference. Like we need to know at the underground what is the volume we have, and when we actually take it to the above the ground, so what is the volume we will get, right? For instance, giving an example in here, like inside the reservoir, the natural gas, for instance, this small amount of natural gas if you actually take it out, then it will be a big amount. Why? Because you are actually decreasing the pressure and decreasing the temperature, so it will become more, volume will be higher. But in case of crude oil, if you actually have this amount, for instance, then if you actually take it out, then probably you will get even less sometimes. Okay, why? Because the compressibility of the crude oil or the oil is lower. Usually it's don't compress at all. Okay, but the natural gas can compress more in higher proportion way. Okay, and also it become lower because the dissolved gas will just go out and vent it out. Okay, so you will get the lower. So these are the informations actually we need to know, and that's why we'll actually develop the correlation. Okay, we need to know how much gas or oil is in the reservoir, and when it actually comes out, then how much the volume it would be, and that's actually we can determine by the compressibility. And how we can do that? We can actually do it by the simple ideal gas law. We can derive the equation through the ideal gas law, and we already know the ideal gas law, PV equal to nRT, right? So I'm not going detail because most of us already know what is the ideal gas law. Now this is just the ideal, but in real situation we actually introduce one factor, the compressibility factor, Z. Okay, so Z is for the real scenario. Now the compressibility factor is defined is the volume of gas. In case of natural gas, the expansion factor the expansion factor, which is the opposite of the compressibility factor, is actually defined as the E is the volume of gas at standard condition divided by the volume of gas at the reservoir condition. That means this is the volume at the standard condition and the reservoir condition, and we can actually reduce it by using these different assumptions. Okay, now there is an example is given. Please go through the example. Okay, and the gas formation factor, or like the compressibility factor, is a totally opposite of the expansion factor. Okay, so it's just the inverse. And what would be the it's a reservoir barrel divided by the standard cubic feet. Okay, so there is an example. Please go through this example, and there's some questionnaire. Please go through that. It could be very important for the quiz and the assignments also. Okay, so please go through it very carefully, and it's really easy to calculate and understand the problem. Now some basic terminology. We have the gas density, so we already know what is the density and how we can actually measure the density. Okay, and like for instance, like the gas density of methane at 2000 psi and 20 degrees Celsius, and the compressibility factor like 0.89. So what would be the gas density where the molar mass of methane is 16? So if you actually use this formula, you can calculate it easily. Okay, so and apart from the density, there is another parameter we need to know, is the viscosity. Okay, so viscosity means it be more viscous. That means if you actually increase the more pressure, that means it could be viscous. So the lower viscosity means higher flow, and the higher viscosity, how we can actually get the high viscosity? By increasing high pressure. But if you increase the temperature, okay, in the case of natural gas, it is high viscosity, which is totally opposite for the oil or like any kind of liquid. If you increase the temperature of the liquid, it would be lower viscosity. Okay, so this is a very important thing to remember. Okay, so this is like the temperature, viscosity, and the pressure correlationship. The same goes with pressure. These are like the varying the pressure, temperature, and the viscosity correlationship for the gas. Okay. Weibull index. Weibull index is the measurement of the quality of the gas, which is defined as the energy density divided by square root of the relative density of the gas. That means for a given portion of the gas, how much energy we can actually extract from that gas, and which is the most important part, because the main usability of the gas is how much energy it could actually provide. Okay, so it's measured in mj, or megajoule per cubic meter, or BTU per cubic foot. This energy density is often referred in HHV, or higher heating value. Okay, so Weibull index, that means the higher heating value. So the more the heating value would be, the better the index would be. Okay, and thus the better the energy we will get. So that means the value or the price of gas, natural gas, is determined through this index. Okay, and this is the example how the energy density and specific gravity actually works. Now there's some question: which gas is considered the highest quality in here? The question for you. Okay, we'll actually hear this at the live session. What would be your answer for it? Oil compressibility. Well, just like the natural gas, the compressibility and the expansion factor we have calculated the same way actually goes to the oil. The oil compressibility is the formula for it. Okay, so please go through the oil compressibility, and as you know, what I have said earlier, like the higher temperature means the lower viscosity, which is very opposite to the natural gas, and it's self-explanatory. For instance, if you can see that, like, I mean, at 4 degrees Celsius temperature, the water's viscosity is highest, right? And if you actually increase more, the viscosity will go down. And for instance, the honey, okay, the honey at a lower temperature is very viscous and thick, but if you actually increase the temperature, then what happened? It will be less viscous. Okay, if you actually increase the temperature of a wax or even butter, okay, at a normal temperature, butter is kind of like a Bingham types of fluid, okay, like, I mean, very, very viscous. But if you actually increase the temperature even higher, like, I mean, 25 degrees Celsius or even more, and like, I mean, 40 degrees Celsius, 50 degrees Celsius, then what's happened? Like, the butter will get melt and it will be lower viscous. Okay, so this is a kind of like real life example for like how the oil viscosity actually works. But in case of gas, the more you increase the temperature, the more the viscosity increase. And why is that? Why that could happen? Because actually, in case of natural gas, what's happened? So it's became kind of like very messy. Well, in case of natural gas, for instance, here, for instance, this is a molecule of natural gas. This is another molecule. This is another molecule. There are like these molecules of natural gas. Okay. Now, if you actually increase the temperature, okay, if you actually increase the temperature, for instance, this is the molecule at 50 degrees Celsius. Okay. But at 100 degrees Celsius, if you actually increase the temperature, okay, so what will happen to the gas? If you actually increase more temperature, then in that case, it will gain the more energy, the internal energy will increase, and then it start moving faster. And when it starts moving faster, then what's happened? It will actually collide, okay, and it will collide with each other, and then it will actually make more resistance of that. Okay, so it became like very, very busy and very messy too. So it will like move, zigzag, and collide with each other, and that's exactly why the whole, I mean, viscosity will actually decrease. Okay, so this is the main reason. So but if you actually give more, if the volume is actually constant, this is the main condition. But if you actually increase the volume even higher, so that these molecules can actually go separate, and that's how the viscosity could actually decrease. But under a certain volume, okay, the gas viscosity will be higher than the liquid. Okay, now the oil formation volume factor. So the oil formation volume factor is a value used to compare the volume of the oil at the reservoir condition versus the volume of the oil at the surface. It's a very important factor because we need to know what is the volume of the oil at the surface, because that's the oil physical quantity we will actually get to sell to our customer or to send to the refinery or to transport. Okay, so this is a very important thing. When you actually estimate the oil, physical oil actually, the presence of oil in the reservoir, that's the quantity, and what the quantity we get in the reserve and in the surface, those are different. We already have explained why it's different, right? So the oil formation volume factor is B naught or BO, which is very similar with the gas formation volume factor, BG. Okay, so we already know this phase diagram. Okay, if you actually go through that, then you will actually see like this is the oil formation volume factor, and then it decreases. Now you see this strange graph. Like at first, this you increase the pressure, okay, but the B naught actually increase, and all of a sudden it start decrease because it is the point where the surface pressure became equals, and that's why this oil formation volume factor actually increased, because the inside the gas inside was expanding, and all of a sudden when it actually go to the surface, it starts decreasing because the gas actually goes out, and you only have the crude oil you have. Okay, so since we already said like the natural gas dissolved in the crude oil, so what would be the proportion of gas would be dissolved in the crude oil will be we actually refer it as with the GOR, or gas oil ratio. Okay, so the solution GOR increased the almost linear manner with the pressure. Okay, that means the heavy oil contains less dissolved gas than than the lighter oils. Okay, here is the example. And how we can actually calculate the solution to GOR? We can actually calculate it this very easy formula. Okay, so here's the thing, like oil under the reservoir, and when you actually take out the solution gas under the reservoir, when you actually take out, and the liberated gas would be this minus this. Okay, so you can get like the how much gas actually went out. The oil density, you can actually calculate the downhole oil density using this formula. Please go through this example, and you can actually pretty much easily calculate the downhole oil density using this formula. Okay, now how we can actually know like what is the composition of the crude oil, because it is very important to know the composition to calculate, like how much is the how much oil actually reserves in there, and that's actually you can do with this PVT test. Okay, the results of this PVT test will contain most of the values that mentioned earlier. Okay, so the PVT test, this is the input of the reservoir simulation, and we'll get the PVT test analysis. Net gross ratio. So this is the formula for it, like the thickness of the productive rock divided by the thickness of the total rock. So from the total rock, there is a certain portion the oil is trapped, so from there we can actually get the net gross ratio. Okay, so this is like the reservoir, the bottom of the reservoir, top of the reservoir. This is like non-productive, or like the shell. Okay, but these are like the sedimentary rocks that are with a higher porosity and permeability, like the oil can be trapped in. Okay, so this is how we can actually calculate the net gross ratio. And probably we have explained about the porosity and permeability already, and how we calculate the porosity, permeability, and this is the hydrocarbon saturation. So volumetric estimation. Volumetric estimation is concerned with quantifying how much oil and gas exist in an accumulation. Okay, this is very important, since we can actually calculate with we can actually estimate from this net gross ratio too. Okay, so there are two different methods. One is the deterministic, another is the probabilistic. So from deterministic method, it's like you remember, like we put like the different sensors after we drill, like the well logs. Okay, so after we send the sensors inside, we actually collect the data, different types of data we actually collect, right? So from those data, we can actually determine how much oil could be inside potentially. Okay, that's what we call the deterministic method. Another method is the interesting one, is the probabilistic method. That means we use the predictive tools, statistics, and now we actually use artificial intelligence to analyze the field data, and then we actually do the estimation based on the statistical input and the data from this data mine, and then we actually develop a model to predict the estimation. Okay, so you'll need these terminologies like the stock tank oil initially in place. Remember this. And another is GIIP, gas initially placed. Okay, and another is hydrocarbon initially placed. That means like the oil and gas all together, hydrocarbon initially placed. So how much we have inside initially placed. Okay, so how we can actually calculate those? We can calculate those by this, using these two formulas, like the stock tank oil initially placed, we can calculate by this. And remember all these values we have seen before. Okay, B naught, S naught, and by G, GRV. So all these values we already know from our previous slides, and here it's the same too. Okay, so from there we can actually calculate the ultimate recovery, which is HCIIP times the recovery factor, and how much left, or like how much reserved. Okay, we already have. There is an example again. Please go through this example and you will find very interesting to calculate. So this is one of the example for how we can actually calculate the amount of reserves we have. Now let's go to our lecture with the estimation. Let's continue with the volumetric estimation. So as we know, STOIIP, or stock oil, is this formula we used, and the unit will get with the standard barrel. And for GIIP, or gas initially placed, is in standard cubic feet. Now we also know GRV is the gross rock volume. How we can calculate the rock volume? If we know the product area and the thickness, then we can actually calculate the volume. Pretty much simple, right? So now in order to calculate like the net sand area here, okay, like the product area, we need to know like the net oil sands actually present. Like in Canada we have the oil sands, so if we know the length of the oil sands, okay, or like so we can actually calculate the NOS, and the water content, how much actually water content in there, and from there we can actually calculate like the whole thing. And how we can calculate? Using area depth method. Okay, so this is the area depth method. So we can have a very random shape of area, and if we know the area and if we can estimate the depth, then we can actually get the volume. Okay, so there is a video you can see how actually this random shaped area calculated by the geologist. But nowadays we actually use computer technology. This is a very old technology they actually used before, like the area of a random shaped contour, how to determine that. Okay, so from there we can actually calculate the area by using the area depth method, and if we know the gross thickness, we can easily calculate the reservoir volume. Okay, but however, this reservoir thickness can vary, okay, because in a very different area the reservoir thickness could be varied differently. So that's exactly why we need to do the geological surveys, and from there we can actually get the data, and from there we can actually estimate how much thickness could be, and from there we can actually generate the area and the thickness chart, and from there we can actually estimate, like we can actually do the integration. Okay, we can integrate the whole area, and we can actually estimate like the how much volume it could be. Okay, please go through these slides. It's pretty straightforward, and you can actually know how we can actually determine the area. So basically it's pretty much it. So we have actually covered like the whole set of like the hydrocarbons. We have discovered the distillation, fractional distillation, and how we actually measure the hydrocarbons, how we actually measure the density, viscosity, etc. and we have discussed about the phase diagrams, the importance of the phase diagrams, okay, why we need that. And then we have discussed about like the crude oil classification, different types of crude oil, the compressibility factor, which is very very important because it gives us the idea about how much oil or natural gas reserves inside if we know the volume. And to know the volume we actually get this estimation, the volumetric estimation. Okay, so this is how it's all actually connected to each other. Okay, so stay well, and we'll actually continue the next topic after we finish everything. Okay, after I mean this topic is I know it's a big one, but it's most of the information probably you know already beforehand. All right, so take care and have a nice day, everyone. Goodbye.